we're going to kind of talk about something that's kind of related to the dynamic fee collection. Going to basically talk about how proof-of-stake security can be related to how much MEV you can redistribute. And in some cases, quite counterintuitively, you can actually have significantly lower inflation rates and subsidy rates. And yeah, so that's what we'll be talking about. So first, a little background. So MEV in a proof-of-stake world actually becomes a lot more interesting. So, kind of, if you were here earlier at the panel, you may have heard Chitra talk about sort of the lack of adaptivity of proof-of-stake being a sort of problem, and sort of there's this trilemma between proof-of-stake and proof-of-work, where you sort of need to know the stake distribution before you're able to actually sample how things change. But on the other hand, because you know the stake distribution, you could redistribute MEV much more efficiently. And things like MEV smoothing, or I guess we wrote this paper before we knew that was the term, so we called it MEV redistribution, but is a lot easier to do in the proposer-builder separated world. Part of the reason for this is that it just makes the cost of off-chain agreements to avoid redistributing some of the MEV to the rest of the stakers significantly higher. Of course, you can't totally remove off-chain agreements. I think you can reason about that. But one of the questions then is, how does redistribution change security properties of a proof-of-stake protocol? And so Abadia and Vemla performed the first sort of analysis of this. Actually, I think it was on one of Elaine's slides. That was a smooth curve. But we want to kind of analyze this more formally. So what is MEV redistribution, MEV smoothing? It's really about redistributing collected MEV, some fraction of it, pro rata to stakers. And while we have no known credible way to prevent off-chain agreements, for now, in this paper, for this analysis, we sort of assume there exists such a mechanism. There are a bunch of ways to potentially do that. Both either directly from how the proposer consensus rules are built, or something like eigenlayer, but we just assume that there exists such a system. And the real question is to understand how it affects security. So what does security actually mean in this case? Well, actually the last time I gave a talk on this stage was about this point about how do you ensure that stake is sticky in proof of stake, that people who are rational, not honest, not Byzantine, don't move their stake from locked in the network to reallocate to DeFi in some way, shape, or form. And this paper showed the sort of non-asymptotic phase transition between scenarios where all the stake stays staked versus all the stake goes to DeFi, and sort of somewhere in the middle where you have this sort of like sort of probabilistic phase transition. Now, one question about moving between staking and sort of DeFi like lending is that lending creates MEV via liquidations. So this is basically, there's a position that's underwater in, say, Aave or Compound, and one of the reasons it creates sort of this MEV is there's sort of this race to submit the first bundle that follows an Oracle update for that price change. You can buy the collateral at a discount and then resell it. So you might say, okay, well, now that we know that there's this one form of MEV, it's actually, in fact, the dominant form of the tail of the distribution. DEX MEV is actually quite small. One question you might ask is, how do we relate sort of yields from staking, yields from lending, and sort of the implied yield from MEV? And so one thing that's been true since about March of this year is that, empirically, is that the utilization and lending rates in almost all on-chain protocols have been quite correlated to future liquidation volume. It's sort of, some type of slight autoregressive model. And so we say, okay, let's assume this correlation holds, because then we can at least sort of reason about how things are going. So now let's just talk about sort of the simplification, like what we do to be able to analyze this. So, this talk definitely won't get into anything that of the proofs. We're just going to kind of state the results and give sort of the notation. So a proof of stake protocol has a token supply, S of k, has a block reward, R of k plus 1. This is the reward schedule. There is an amount of protocol-owned liquidity, epsilon of k, that is either burned, so that means EIP 1559, something of that form, or it's protocol-owned. It's a protocol where basically the DAO treasury takes some fraction of each block reward. And we have sort of this natural dynamics. So there are n agents. They each have a portfolio. Their portfolio consists of coins, some allocated to staking, some allocated to lending. And effectively, you can compute the total stake supply, the total lent supply, and the total protocol-owned supply. So that's L, lent, T, staked, epsilon, protocol-owned. Lending yields. So lending yields, we model this just strictly off how compound and Aave's interest rate curves are constructed. The lending yield is given by this following update. In this case, we use a linear model based on utilization. The utilization in any DeFi lending protocol is the total amount demanded of borrows divided by the sort of total amount in supply. And we, for analytic tractability, assume that there's sort of a constant demand relative to the market supply. But in simulation, we simulate with more complex demand schedules. And I'll let Kshitij take from here.
Cool. So I think the next step is to model the MEV. And I think as Tarun said, sort of the crucial assumption here is that lending yields now are correlated to MEV at some point in the future. So this is sort of the idea that liquidations in MEV, lending right now causes liquidations in the future or something like that. And so basically we model this as this sort of regressive process where Q at k plus 1, which Q of k is the amount of MEV extracted at time k, is correlated to MEV, positively correlated to MEV at some, it's correlated to lending yields at some time in the past. And for simplicity, we can just assume that that time in the past is 0 units of time in the past. So you get an equation that relates yields right now to MEV in the next step. So how do we already introduced the lending yield. Now for the staking yields, the agents choose portfolios, and their staking yields are basically the reward schedule of the proof of stake protocol plus this added MEV component distributed pro rata to the stakers. So you bucket all these tokens up, and then you distribute them according to their staked portfolios, and that's all this equation is saying. And so now the question is how do the agents sort of choose their portfolios? And if they're sort of economically rational, they should be choosing portfolios in a way that, in some sense, matches sort of the risks that they're taking in staking and lending. So to do this, we sort of introduce 3 additional parameters in the model. One is the the risks that they're taking for staking and lending, which is given by this fixed in time covariance matrix sigma, whose entries are, say, just drawn from some exponential distributions that indicate their risk preferences over time. But these are fixed. And then they use this covariance matrix and the return vector that they observed in the last time step, along with the risk parameter lambda that says how do I want to trade off between the return and the risk. And they solve at every time step a mean variance optimization problem. And so this optimization problem basically says I want to trade off some amount of return for some amount of risk, and each agent is solving this over their portfolios, which are allocated to staking and lending. And it turns out that you can give an analytic solution to this optimization problem that every agent is solving at every time step. So once you have this solution, you can plug it back into each agent's update for their stake portfolios, and now you get sort of a bona fide feedback system. So the only variables in the system are the reward schedule R of k plus 1, and what the protocol is going to decide to be burned or protocol and liquidity. But this is truly a feedback system. It's a deterministic system that takes staking yields and lending yields for every agent at time k and updates them at time k plus 1, assuming that these agents are solving a mean variance optimization problem. And so the states of the system are the n staking yields for all the n agents plus the 1 lending yield. So it's an n plus 1 dimensional system. But one thing that you can note is that alpha, this fraction of MEV that is redistributed to the stakers at every time step, shows up in these dynamics. And basically the goal is to understand how the system behaves as alpha changes. That's basically the sort of the punchline of the paper. So I'm just going to now do 200 years of dynamical systems in 2 slides. So what is a dynamical system? A dynamical system is just you fix some initial condition, which could be a number. In our case, it's a vector. And you have a rule for updating the state over time, given by this function f. And in particular, we're interested, because here we're trying to understand how alpha, this parameter that's shifting these dynamics at every time step, affects proof of stake security. We want to understand the behavior of this of a dynamical system around an equilibrium point. And so what's an equilibrium point? It's a point where if you plug that point into the system, so if you take f of that point, you stay at that point forever. So you're never moving from that point. That's an equilibrium point. And then we need sort of one more definition, which is the definition of stability. So stability means, roughly speaking, it means that if you have an equilibrium point somewhere in the state space, if you start close enough to that point, you will end up reaching that point as time goes to infinity or in some amount of time. And so there's one more concept that we sort of exploited in this paper to characterize how this system behaves under a particularly bad equilibrium that I'll mention in the next slide, which is this notion of linearization. And so what this says is if you have a dynamical system, which is given by this function f, you do one of the stupidest things that you can imagine doing. You take its Taylor approximation, you throw away all the higher order terms, and you create a linear system from that dynamical system. So you take the first order approximation, you throw away everything else, and it turns out that some properties of that linearization tell you a lot about the stability of the nonlinear system at this equilibrium point. In particular, if the eigenvalues are smaller than 1, then the nonlinear system is stable. It's the eigenvalues of this linearization. If the eigenvalues are bigger than 1, then it's unstable. And so coming back to staking and lending, we have this dynamical system. So what's the really bad equilibrium point here from an economic security perspective? It's the point when staking goes to 0, or the staking yields go to 0 for all the players. So mathematically, this means that these gamma I s's are going to 0 identically for all I. And so one thing you can verify is that this is indeed an equilibrium point. So if you plug this point in, there's some lending yield at which this equation is satisfied. The equation that if you plug it in, if you take f of x star is equal to x star. So this point is an equilibrium point of these dynamics. And it's really undesirable because it basically means your security system the proof of stake security has crashed and your system is no longer useful. And so we want to avoid this equilibrium point. So how do we do this? The basic idea is make alpha large enough such that you make the linearization of the system unstable. So you force the eigenvalues of the linearization outside of being magnitude less than 1. And if you can do this, then this equilibrium point, this bad equilibrium point, is unstable. So sort of the basic insights here are if you make alpha large enough, you can avoid this bad equilibrium point. That is, and sort of economically, this means that if you feed back enough of the MEV and distribute it to the stakers, you can sort of force them out of this sort of very undesirable equilibrium from a security perspective. But there's another interpretation, which is if you fix an alpha, if you fix an amount to redistribute, the reward schedule that you need to achieve this this sort of instability of this bad equilibrium point is going to be less than what you would need if alpha was 0. That is, you don't need to inflate your token as much or at as fast a rate in order to make this equilibrium unstable. And so we did some simulations, and sort of it turns out that in many sort of inflation rates, so in many rates values of R, and in sort of many instances, you can in fact avoid this equilibrium point. So that is, and actually these simulations are even stronger, which is what they show is that you actually end up going away from this equilibrium sort of it's not even asymptotic, like in a finite time you can escape, and move to sort of here, in this case, the all staking equilibrium, so no one's lending, but it's effectively, or close enough to no one lending. You can't actually reach there. But yeah, so the punchline is you can use MEV redistribution to sort of avoid these bad economic equilibria that occur in these proof-of-stake systems, and to do this, you require actually less inflation or sort of lower inflation rates than otherwise necessary. And so I will just leave you with this meme, and happy to take any questions.
Hi. Just a quick question. Do liquid staking derivatives drive down the alpha requirements at all?
Yeah, good question. So there's a paper in between these two that reference me and Alex Evans that does show that they do that. They do have this bad port. They basically do reduce the Gini coefficient at the expense of like kind of increasing the slashing rate. So there's sort of some trade-off when you have liquid staking derivatives. The main point here, I think that's more interesting than staking derivatives, is that this MEV redistribution, MEV smoothing, is actually this like feedback control system, right? You took this like very deterministic, like Dirichlet process looking thing, and you added in this feedback mechanism. And the feedback mechanism actually gave you exponentially less inflation needed. Like one of the previous slides actually shows that a deflationary inflation schedule, even though you might have to give more MEV back, so that's the top left corner, a deflationary MEV schedule, so that's like a deflationary inflation schedule, that's like Bitcoin, can actually avoid this bad thing if you redistribute. That's not true with staking derivatives.
Well, if you combine the two, could you drive the inflation rate even lower though?
Yeah.
Okay.
That we suspect, like the fact that you can go to fixed supply event asymptotically with MEV redistributed. Now, of course, this assumes this sort of positive autoregressive model for lending, right? And that's not always true. And also, of course, there's many other types of MEV, right? It's only the third largest type of MEV. But the idea that, it must have passed, yeah. This thing assumes beta p is greater than 0 for all p, or greater than or equal to 0 for all p, and there's at least one p for which it's greater than 0. And that's not always true, but that has been extremely true this year. So.
Yeah. Okay, makes sense. Thanks.